Okay, so this is our wind turbine. Our wind turbine has radius of 8.5 meters. The point sweeps 30 meters from 3 o'clock position. And we just found that the angle in radians therefore would be 30 over 8.5. We want to know how many radius lengths of length 8.5. Brighter. What's going on? This is the second one, right?
Yeah, that's the one I've been using lately.
It's not working.
Try the third one.
Okay, that's the fourth one, I guess. Okay, so we want to know if 8.5 is the length of the radius, and we go 30, we want to know how many 8.5s make up 30, because that'll be how many radius lengths, like counting radius lengths. We know the number of radius lengths is the same as the openness in radians, right? So this is about 3.5, and that's what I'm showing in this picture. Okay, now we want to represent the vertical distance above the horizontal diameter as a fraction of the radius length. Walden. He wants sine of 30 over 8.5. Would give us the vertical distance above horizontal diameter in radius lengths. Agree? All right, is this positive or negative?
Negative.
Because it's below. So do we need to put a negative sign on there? No, that's what sine automatically does it, right? Sine automatically gives us positive if it's above and negative if it's below. That it automatically has that built into its meaning. So you don't have to put the negative on, okay? What about, so that's our vertical distance above horizontal diameter. And then horizontal distance right of vertical diameter. Hamid. Cosine of 30 over 8.5. And now if we want the coordinates of that point, and all I told you was the coordinates of this point were 8.50. So that's the only information you have. And you want the coordinates of that point. Yeah, Christopher. He wants to multiply both these by 8.5. Yeah, because we want, if these are fractions of a radius length, and now we want it in meters, we want to take those fractions of what number? Of the radius. All right, so which one comes first? Cosine. 8.5 cosine of 30 over 8.5. I tried to leave her a lot of room. Will I have enough? And then the y-coordinate? Sine of 30 over 8.5 is a fraction of the radius length. And we want that fraction of 8.5. So we just multiply by 8.5. All right, now let's estimate those values. So, well, you've already found them in your calculator. So that exercise is kind of moved. But how about if I estimate them? Because I haven't done that yet, and you see what you think. So, in terms of cosine, it looks to me like it's pretty much all the way to the farthest left it could be, maybe a little bit less. So I'll say negative 8.4 is my guess, okay, for the cosine. And it's to the left, so it's going to be negative. And then on its way down here, it looks like about a quarter of the way down. So I'll say, but it's down, so I'll say negative 2.2. Negative 2.2 for the sine. So that would be my reasoning for estimating those points. Now use your calculator. Was I close? Okay, actual is? Or much better approximation? Negative 7.87. -7.9. Ooh, I wasn't very good at there at all. Okay.
Negative 3.2.
What? I'm off today. So apparently that's, oh, you know why? I have a good excuse. Because this, the position is actually somewhere between here and here. That's why. So, okay, anyway. And these are in meters now. And those are the coordinates of the point. Okay, so this is what sine and cosine does. It lets us find position or points, the coordinates of points on any circle, right? Any circle, because it generically gives us those results in fraction of a radius length, so therefore it applies to any circle. Once you have your radius, you're just taking those fractions of your radius if you want that position in whatever your length unit is. Okay, so that's review. Any questions on anything we did today so far? Really important stuff. Okay, so let's look at this unit circle a little closer here. And where did it all begin? It all began with looking at taking the radius. It all began with taking the radius of a circle and peeling it off its normal spot and wrapping it on the circle, keeping its length as one radius length, and that gave the angle that arc then defined an angle that was what? 1 radian, right? Radians of openness comes from radius lengths of arc length cut off by the rays. How many radius lengths of arc length cut off by the rays gives us that openness in radians. Okay? And so then we said we could keep counting around, and this would be 1 radian of openness, and then if we added another radius length onto the arc length, we'd have 2 radius lengths of openness. And continuing on that way, 3 radians, 4 radians, 5 radians, 6 radians. Okay, but we said that, what about these positions on the circle? Are they convenient positions? Are they helpful? No, they're just kind of, they're not in places that are kind of symmetric with our axes and with the top and sides of the circle. So it'd be really nice to have values that were based on symmetry of the circle and the grid system. Okay, so where did that come from then? Right, so we said let's figure out how many radius lengths gets us exactly halfway around. And if we know exactly halfway around, we could have nice symmetric places on the circle based on that. And so halfway around is how many radius lengths? Pi, right? Pi was exactly halfway around. And so based on pi, so 3.14159, to get it exactly halfway, then you need every single decimal point on to infinity, right? But 3.1416 gets pretty dang close. So even if we just take 5 or 6 decimal places, we get very, very close to the number of radius lengths to get halfway around the circle, and therefore the number of radians of openness, okay? So from pi, then, we can start building, like I said, we could break up the circle so that we pinpoint convenient locations based on symmetry. So the first thing we do is we could do fourths. So we can break up the top into fourths, and then continue on around the bottom of the circle that way. So to know these angles, all you have to do is count. Just count number of fourths. Okay, so watch, ready? So here's 1 pi over 4. 2 pi over 4. 3 pi over 4. 4 pi over 4. 5, 6, 7, 8. So all you have to know is Where is pi over 4? And then you just have to know how to count. 1, 2, 3. So then we look at the top of the circle. Is that, or let's say the left side, 4 pi over 4. Is that right? Yeah, because that's just pi, right? And then 8 pi over 4 for a full rotation. 2 pi. So you count around by fourths, and then the ones that are at the top and the bottom and the left and the right, those will simplify to pi over 2, pi, 1.5 pi, or 3 pi over 2, and 2 pi. Okay, so that actually gives us 4 new angles, the fourths. Okay, so pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so I want you to find the value of 7 pi over 4. So estimate 7 pi over 4 using your calculator. What'd you get? About 5.5? What does that number mean? About 5.5. 5.5 what? Radius lengths to get around. So what happens with this when we start getting all these symmetric angles and memorizing, I think what happens in students' minds is they just think that these points on the circle are like, these are the labels for those points. Like 7 pi over 4 is just the name of this point, right? It's just a label that tells you that point on the circle, halfway up in the fourth quadrant. But no, 7 pi over 4 is a number. Don't forget that that number is how many radius lengths it takes to get around to that spot. Okay? It's not just what we're going to call this point as a location. It's not just a label or a name. It's a number. It's a number of radius lengths from the 3 o'clock position around. Or the openness, right? The openness of an angle. 5.5 is the openness of an angle, swept counterclockwise from our positive x-axis with a terminal side here. Okay, so just remember that when we're going to start throwing all these symbols on the circle, they're not names, they're not labels, they're numbers. They're numbers of radians, openness of angles. Okay, so then from there we could do our, or let's see. Oh, we'll do that later. Okay, so what about the, maybe, wow, it's jumping down on me. I can't get it. Okay, so then the next thing we need to do is take the pi that we started with over here, pi, and divide the top into 6 equal things. So we know this is pi here. So let's divide the circle up into 6. Let's get rid of these here. Okay, so here's pi again. The red ones, we already got. Those are our pi over 4. Now let's do 6. Same thing, you just count, right? You just start with the first one. 1, 2, 3, but now we're counting by pi over 6. Okay, so here we go. Watch it. Ready? 1 pi over 6. 2 pi over 6. 3 pi over 6. 4 pi over 6. 5 pi over 6. 6 pi over 6. So the way you can remember these angles is just by counting. You just count. You just have them in the right spot and you just count one at a time. So then that's 6 pi over 6, and then 7, 8, 9, 10, 11, 12. Okay, and then some of those will simplify. Some of those will simplify. Of course, we already got 3 pi over 6, pi, 9 pi over 6, 12 pi over 6. Those we already have. So we have these new ones within each quadrant. And so the first set of new ones, oh, not yet. Let's see here. These do not simplify. So these, it's pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay? Those are in fully simplified form. So those are our pi over 6 angles. But then you notice that these 2 pi over 6, 4 pi over 6, 8 pi over 6, and 10 pi over 6, those all simplify to thirds. Okay? Those all simplify to thirds. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay, so any questions so far? So again, remember, to do the pi over fourths, pi over 4, so you start here, you're just splitting each quadrant in half, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8 pi over 4. Just count. And then for pi over 6, you split each quadrant up into 3 parts. So 1 pi over 6, 2, 3, 4, 5, 6, 7, 8, 9 pi over 6, 9 pi over 6, 10 pi over 6, 11, 12. And then you simplify the ones that can be simplified. So then what you end up with is you end up with 4 new angles that are divided by 4. Those are the ones I have in red. Maybe. 4 new ones that have 6 in the denominator. Those are the blue ones that I have. And then 4 that are, I have it kind of in purple color there, that are divided by 3. And so we call these the 16 key angles. Because they break up the quadrants either in each one in half. The pi over 4s break the quadrants in half. And then the pi over 6 and pi over 3 angles break up each quadrant into thirds, equal openness of thirds. So we get the 16 key angles. But remember, they're numbers, right? They're not just labels for points or names. They're numbers. Okay. So then the question is, let's look at this right here. This point right here. Estimate the sine and the cosine, estimate, of pi over 4. So the coordinates of this point would be cosine pi over 4, sine pi over 4, and those coordinates would be measured in what unit? What unit are we talking about? Fractions of a radius, right? Or radius lengths. Not radians. Radians is the openness of an angle. Radians is the openness of an angle. So we either say radius lengths, or we could say for sure it's going to be fraction of a radius. So what do you estimate based on the picture? Estimate these coordinates. Estimate these coordinates. What would you estimate cosine to be? What would you estimate the sine to be of pi over 4? What's that? She said 0.8. Okay, pretty good. Actually, it's small, but the numbers are on here, so we can do a little better than 0.8. But you definitely know what you're talking about. So here's 0.8 right there. That's 0.8. That's 0.6. So it's looking like 0.7, right? So we're thinking about 0.7. What about the sine of pi over 4? Okay, so approximately the same number. Why does it make sense that those should be approximately the same number? Because we're going halfway up in the quadrant, right? So if we go halfway up by symmetry, then we expect the same x and y coordinate. All right, so now we want to find those exactly. So how can we, so we're guessing by the picture that we're about 7/10 of the way to the right and about 7/10 of the way up as a fraction of the radius. But we want to get those exactly. How could we get those values exactly? Not use your calculator. We want to like prove it, right? We want to prove what those are without just putting them in the calculator. What's that? But where does that come from? You need to memorize that. someday. Sometime in the past you learned that. But where does that come from? Okay, so I'm going to, in order to kind of figure this out, yeah, so if I extend this from the origin up to this point, and I look out to there and there, I was so close. Okay? So we can use a triangle to actually get these values. Okay? What's this length right here? I heard the hypotenuse, I heard 1, I heard the square root of 2. What is the length of that side? Which is? Yeah, everything, all my scale here is in radius lengths, right? 0.2, 0.4, 0.6, 0.8. So there's no question that this is 1. My unit, this is the unit circle. My units on the axes are radius lengths, or fraction of a radius. So that can't be anything but 1. That can't be anything but 1. All right? How would you represent the length right there? What is that length right there? How would you represent it? What would you say? No, how would you represent it exactly? I want to know exactly what that is. That's the cosine, right? That's how far we are to the right. And we got it in fraction of a radius, so that'd be cosine of pi over 4. What's the height of the triangle? Sine of pi over 4. And because of symmetry, what about those two values, cosine and sine, cosine of pi over 4 and sine of pi over 4? They're the same, so we can, if we want to figure out what those are, because of the symmetry, we can say, oh, they're both, just call them A. So for the angle of pi over 4, the base and the height are the same because of symmetry of that angle. How are we going to solve for A? You're all thinking it but not saying it? No, we want to get, no. So that's how we represent them. We're trying to solve for those values. We're trying to get those values. Yeah, Danny? No, because our radius is 1. Our radius is 1. Yeah. Yeah, because that's our cosine and our sine is A, both A. Right. This is a right triangle, right? So A squared plus A squared equals 1. So therefore, 2A squared is 1. A squared is 1/2. And so A is square root of 1/2. And more often that is, we multiply the top and bottom by the square root of 2. We get the square root of 2 over 2. Put that in your calculator. Square root of 2 over 2. We're expecting it to be very close to points. We expect it to be very close to 0.7 according to what we're looking at. 0.707. That's a better approximation. But that's also an infinite decimal, right? That's an irrational number. Okay, so that gives us, so now we have the cosine and sine of pi over 4. Exactly, square root of 2 over 2. So we showed that with this triangle here. So just saying it's close to 0.7 is not enough. We need it exactly. So as an exact value of sine or cosine or fraction of a radius length, square root of 2 over 2. Okay, so now let's estimate for pi over 6. Tell me an estimate for the cosine. Estimate for the cosine. Let's see here. Braden. What would you estimate the cosine to be here?
Classified as 8.9.
0.9. And how you seeing 0.9?
Is it after 0.8?
So here's 0.8, and here's 0.9 right here. So you want to go with 0.9? Yeah, it's like 0.85, right? So something between 0.8 and 0.9, right? So about 0.85. Okay, what about sine? Jessica, what would you estimate sine to be? What would you estimate the sine of pi over 6 to be? The sine, right? Sine wouldn't be in terms of pi. What is our definition of sine? What's that? 0.5. She's saying 0.5. So look in here. Here's 0.4. Here's 0.6. How about her estimate of 0.5? Yeah, it looks like it looks really close to 0.5, right? It looks like it's right on it. Okay, so what I'm going to do is I'm going to tell you that the sine of pi over 6 is indeed 0.5. You just memorize, just things you memorized. You just memorize that. Okay, so sine of pi over 6 is 0.5. Based on that, I want you now to find the cosine, not with your calculator, not something you memorized in the past. Precisely prove what the value of cosine of pi over 6 is. I just told you that sine of pi over 6 is indeed 0.5. So we want to get an exact value proof of what cosine is. Go, work it out.